So in the last video, we talked about how the evidence is really very clear now that generalized epilepsy is primarily a genetic disorder. It's not a Mendelian genetic disorder. It's not caused by one bad gene, but rather a collection of risk factors, um, genetic risk factors that make it more and more likely for you to have epilepsy. And if essentially you get dealt a bad hand, this collection of these genes, then your likelihood of developing epilepsy becomes very, very high. But what, and that's useful. That's important to know. Um, but for somebody like me that is interested in how brain cells work and how brain cells work together to create the human experience, it's not a super satisfying explanation, right? It doesn't give, beyond genetic counseling, it doesn't allow us to cure epilepsy any better, and it doesn't allow us to understand how the brain has gone wrong to cause epilepsy. So again, I want to go to sort of a classical idea. Oh, this is this is such a classical idea, right? This idea has been around since like the 30s, okay? Uh, Maybe that's a little early, since the 40s, okay? That there's the brain works, right, in some normal range where inhibition and excitation are roughly balanced, right? So maybe when you're super excited, super paying attention, you have a lot of inhibition and a lot of excitation, while if you're sort of kind of bored or not paying attention or just watching TV, you have a low amount of inhibition and excitation, but again, they're still balanced. And that if something then causes the amount of excitation, so this is essentially glutamate release, to outweigh the amount of inhibition, then you get epilepsy. While if you get the inverse and too much inhibition and not enough excitation, you get loss of consciousness. Oh, it's just the worst, right? To try and boil the entire brain down into some kind of two-dimensional plot. Um, and look, this is not nobody didn't just made this up because it sounded good, right? It is based on a lot of observations, right? And we see them on the right here. So drugs that block inhibition, that block GABA A receptors, they cause seizures. This is a fact. Okay, drugs that enhance um, GABA A function can prevent seizures, and if you give too much of them, can lead to loss of consciousness. Okay. Um, it's also true that drugs which enhance excitation, so AMPA agonists, they can cause seizures. All right. So there's some kind of truth in this. But on the other hand, some drugs that enhance GABAergic transmission can make absence epilepsy worse. And it's you're going to see that it's just too crude of an idea. Okay, it's too crude to think that the brain is just sitting there basically, that the point of inhibition is to vaguely reduce excitation or to balance it out, right? There's more going on here than this. Though, if this is your only way of thinking about epilepsy, I suppose it's better than nothing. Okay, so what is happening in the brain? Let's look um, into it. And the first thing we're going to do is just look at an in vitro model, so a brain slice model. So you anesthetize an animal, you remove its brain, you cut the brain into fine slices, and then you can get electrical access to cells. And you give this drug 4AP, which blocks various potassium channels, voltage-gated potassium channels, and a seizure or a um, or a seizure-esque event happens, and this is what you see, right? So this is using a local field potential electrode, right? So this is like EEG, so you only see something on the LFP if there is a lot of synchronous activity. And so you can see that all we've done is given 4AP, and we get this huge, this nearly goes on for a minute, pattern of synchronous activity. So we're going to call this, a seizure model, an epilepsy model. Now, we can talk about how good or how bad this is, right? So for instance, reasons that this is a good model. So here, this is 20 minutes now. So each one of these downwards lines is one of those seizures we saw before. And you can see here's a relatively new anti-epileptic that I've sort of been familiar with its development. And you can see that when you give it during this dark period here, the seizures stop. Some people would get very annoyed at me calling them seizures because they're not true seizures. This isn't a brain slice. There's no animal, right? But we're just going to call them seizures for ease, right? So you give an anti-epileptic drug that we know that when you give it to people, it stops them having epilepsy, and these seizures end. So what's happening inside the neurons? Well, what we see is that they are hyperactive before we see a seizure, right? So neurons in brain slices are nearly always silent. They don't fire action potential spontaneously in general. This is not always true, but in general, they're silent. Um, but when we've given this 4AP drug, we can see the neuron is firing action potentials constantly. Then just prior to the seizure beginning, we see this what's called a paroxysmal depolarizing shift, which is basically the membrane potential rising by about 30 millivolts. In fact, it rises so far that we enter something called depolarizing block, which is basically the membrane potential is so depolarized all of the voltage gated sodium channels are inactive, so um, the action potential can't happen, and then this paroxysmal depolarizing shift disappears, the action potentials begin, and then this is when the synchronous activity occurs. Now, what does this really tell us about what's happening in the brain? Well, it tells us a couple of things. One, it is possible, though not certain, because this is just a model, right, that there could be significantly abnormal brain activity prior to the seizure in somebody with epilepsy. That's probably the most important takeaway from this, right? And this, of course, speaks to what we know about EEGs. EEGs can only pick up synchronous discharges. So even if there's a lot of abnormal activity, so long as the neurons aren't firing at the same time, you don't see anything on the EEG. But we see some other important, really important things. So here is an intracellular recording from a pyramidal cell, from a glutamatergic cell, and you can see again, here's the extracellular LFP. The neuron is highly active. Then you see the seizure begin, and the activity pattern changes. So here we see the paroxysmal depolarizing shift, but importantly, this is a recording from an interneuron, a GABA releasing neuron, and we see that it is also hyperactive before the seizure and becomes incredibly active during the seizure. Now, some people will even claim that this these interneurons are in fact very, very active at the beginning of the seizure. And this is what they're trying to illustrate here, right? That right at this point, sort of prior to the seizure beginning, which is when the LFP changes, this glutamatergic neuron is, well, it's the most silent it's been in some time. But if we look at the interneuron, on the other hand, it is being incredibly active during this beginning phase of the seizure. So there are some people that believe actually it's interneurons becoming hyperactive that begins the seizure. Now that may seem incredibly strange, right? If you've just got this idea that interneurons are inhibitory and they make cells stop firing action potentials, but things don't always behave like how they should, especially when you're talking about neurons whose membrane potential is probably jumping 20 millivolts and firing at such high frequencies that you can't even see the individual action potentials. You just get this black blob, okay? Um, and here is sort of more hard and fast proof. So here is a scientist using optogenetic activation of parvalbumin positive interneurons, right? So this is the light pulse, and when they begin the light pulse, that triggers the seizure. So they're driving the interneuron to be active, and the seizure begun. Though you can see here, even prior to the um, prior to the interneuron being active, these neurons were already hyperactive because there was already 4AP in there. So this is where things get complicated, that possibly this idea that lots of inhibition stops the seizure is true in the sense that it can prevent this hyperactivity starting, but on the other hand, once the hyperactivity has begun, then this drive from the interneurons may be what triggers the actual seizure. But how, you might be asking, how can an interneuron start a seizure? Well, when neurons, when inhibitory cells are incredibly active, strange things start to happen, right? So we talked last semester about this idea that we generally make assumptions that the ion concentration inside and outside a cell are constant, and the only thing that changes is the conductance, um, well, and the membrane potential. But when neurons become so active, so depolarized, so they're depolarized, so there's a huge change in the way the ions are flowing. Specifically, potassium is going to be leaving the cell in very large amounts. Um, we're going to see chloride go into the cell because the membrane potential is very depolarized, which allows chloride to move into the cell, but also there's going to be a lot of GABA being released. And what we start to see is that um, a huge increase in chloride inside the cell during these seizures. Also, a very interesting change in pH, which is a whole nother thing, right? But what you can see here is that during the seizure, the chloride inside the cell has gone from 6 millimolar to 26 millimolar, while outside the cell, it's gone from 2 millimolar to zero point 0.1 millimolar. And what that means is that in the cell, E chloride, the reversal potential for chloride, the equilibrium potential for chloride, started at about 80 millivolts, but during the seizure, it went all the way to minus 40, which is nearly, or it's close enough, the threshold for action potential generation. So what that means is during the seizure, GABA became so depolarizing it could trigger epilepsy. It could trigger action potentials. And now we start to have a plausible concept for how seizures could begin. Right? Seizures could be caused by hyperactivity leading to a shift in the um, the equilibrium potential for chloride, so that even the built-in mechanisms for uh, damping down hyperactivity, i.e. the GABAergic system, becomes depolarizing. And so if both glutamate is depolarizing and GABA is depolarizing, and of course with this huge buildup of potassium outside the cell, that means that the potassium equilibrium potential is going to move closer to zero. All of the ion channels in the cell are sort of have turned out to be depolarizing influences, and no wonder that leads to this huge paroxysmal depolarizing shift and hyperactivity. There's a very attractive theory, though how true it is, uh, hard to say, right? And so this is what I want to show, these figures here, okay? So we're still on this idea, which is just basically seizures are caused when the brain is too active. And this idea is simply not supported by facts, okay? It's just not supported. This figure here is going to straight away make you at least realize that in some people it's not true. So this is a recording, a single unit recording from a human with real focal epilepsy. They have a silicon probe, that can pick up hundreds and hundreds of neurons in the focus. And what do they see? Well, they certainly don't see too much activity, right? So here is just neurons sort of roughly grouped into similarity of their response during the seizure. And what we see is that the vast majority of them are less active during the seizure, certainly at the beginning of the seizure. Now, some of them, these ones up here, become sort of hyperactive relative to prior to the seizure. And then amazingly, they all become silent for about 30 seconds before vaguely normal activity happens. Now, I've said before that you can only pick up signals on the EEG when there is synchronous activity, a couple of neurons, 100 neurons, whatever it is, firing at the same time. But while that must be true in the sense of um, uh, if you see an EEG pattern, then there is synchronous activity. What we don't see is this wide spread that all of the neurons in the focus are firing at the same time, right? That there is no great evidence for wide scale compulsory synchrony. And in fact, it may only be a very small percentage of neurons that are firing synchronously, and most of them are just suffering under the influence of these. Or it could even be that the synchronous activity is completely unrelated, that it's some phenomenon that happens during the seizure discharge, but is not causally related to the seizure generation. But it gets even more interesting because you will even find this written in papers, the idea that during the seizure there is unpatterned activity, that there's sort of random activity, that the brain has gone, instead of being some sort of finely tuned machine, is like, like a radio tuned to static, that it's just random hyperactive behavior. Look at this. So this is from that same patient. These are two seizures. Now, it's going to take you a while to see what I'm talking about, but as the more you look, the more you see that the neurons are actually firing in the same way in these two seizures, right? So look at this very first neuron. Right at the start of the seizure, it has a little silent period and then becomes active, right? There's the little silent period before it comes active. The same with another wee collection of ones here. They go for a little silent period, then become active. Look at this guy here at about neuron 70, right? Highly active, chatter, 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 silence during the beginning of the seizure, and then hyperactive at the end. Same thing over here. The more you look, the more you see that there is a huge amount of similarity from seizure to seizure. So the the activity is not random or crazy or unpatterned. Now, on one hand, when you think about it, the brain is you know wired up. It's a physical system. It's a largely deterministic system. So of course it makes sense, right? That um, if you do the same thing to a deterministic system, you should get the same output. But this is very radically different to the idea that people have classically had. So again, you can see that there's not a huge pattern of synchronous activity. There's not, because which, just for the record, that here we see a pattern of synchronous activity, right? All of these neurons, for whatever reason, have all fired an extra potential at the same time. And I'm sure if we looked on the EEG, there would be a nice little blip at this point. But in general, there's nothing going on here. There may be patterns of periods of synchronous hyperactivity, but the actual potentials themselves aren't synchronous. And here we see a synchronous hypoactivity, synchronous hyperactivity, right? So again, it comes down to, we really need to be careful of what we're actually talking about, that we use these terms like hyperactivity or synchronous discharges. What does that truly mean? And what it certainly we can see from here is it doesn't mean that huge populations of neurons are all firing active potentials at the exact same time. Right, so let's just sum that up, right? So it seems highly likely that the majority of epilepsy is due to genes, some due to de novo mutations, but a lot of it due to polygenetic inheritance, right? And that on the other hand, Mendelian inherited epilepsy, one gene that gives you epilepsy, is very rare. We still don't really know what's happening on the cellular level, but we certainly know that probably a lot of our old ideas are wrong. But the idea that it's sort of too much excitation or too much activity or too little inhibition, right, is far too simple. That there could be complex interactions between changes in equilibrium potentials, the sort of the order in which neurons fire, how they're firing, what the exact pattern is. It could set up sort of resonant loops of activity rather than just some simple too much action potential is bad. But honestly, we still really don't have a very good clue about exactly how these polygenetic mutations lead to some abnormal pattern of brain activity that then leads to a seizure.